Let's define who is a troubleshooter. According to Merriam-Webster, a skilled worker employed to locate trouble and make repairs in machinery and technical equipment. As we compare a typical troubleshooter to a scientific troubleshooter, you'll note that a typical troubleshooter will act upon learned behavior, will rarely document anything, and will avoid speaking in specifics. Now let's define science. According to Merriam-Webster Dictionary, this is the state of knowing, knowledge as distinguished from ignorance or misunderstanding. So what is a scientific troubleshooter? A scientific troubleshooter combines both science and troubleshooter and results in a skilled worker who acts from a state of knowing. Let's talk about how a scientific troubleshooter acts. A scientific troubleshooter will know the history of the process, mold, machine, material, and technology, determine what's changed, will act on knowledge, and will verify the results of any change. A scientific troubleshooter relies on process documentation. So now, as a scientific troubleshooter, let's look at machine inputs versus process outputs. As you can see from our little animation, inputs are the parameters and conditions fed into the process. Outputs represent data and information that can be obtained from the process. As we get into the discussion about the importance of process documentation, you'll note that setup technicians most often document machine-dependent settings or parameters, such as injection speed or transfer position. A scientific troubleshooter will document machine-independent outputs, such as temperature, times, plastics pressures, weights, and any additional data that's relevant to the process. Please be sure that you take note of this important difference between a setup tech and a scientific troubleshooter. In the next few slides, I will give you some more examples of what you may want to take note of. As an example of a process output, let's talk about temperature. You should always record the actual plastic melt temperature along with the coolant temperature in and out of the mold. Another example that a scientific troubleshooter looks for specifically are items such as fill time, pack time, hold time, gate seal time, cycle time, and recovery time. When looking at process outputs for pressure, always record the actual pressure applied to the plastic. Please note that a scientific troubleshooter always focuses on machine-independent parameters such as plastic pressure, rather than hydraulic pressure, which is machine-specific. Always ensure that you document the weight of the part. This documentation should take place after fill, after packing, and after the hold is complete. You should always conduct a part weight study to determine when gate seal actually takes place. This will ensure that you're using the appropriate hold time. Every molder and process has specific information recorded. For example, things like cavity measurements, quality measurements, clamp tonnage, photographs, any kind of observations, and how the cavities are balanced. To reiterate, the scientific troubleshooter uses documentation to know how the process ran, determine exactly what changed, act on knowledge, and verify the results. The typical troubleshooter usually asks, what buttons do I push to correct the defect? This is exactly what we're trying to point out to you, is not to get into this type of a habit where a typical troubleshooter will often rely on learned behavior or troubleshooting guides. This is why you hear documentation stressed throughout this presentation. People claim that documentation is important, but they just don't get around to doing it. You'll see in the following examples why good documentation can help you easily identify the source of the problem. First, we're going to talk about flash. When looking at a defect, we want to determine what has changed from our documented standard. So in this case, if flash was a result of a high melt temperature or degraded polymer, you would most likely see a drop in plastic pressure at transfer from fill to pack. And you'd also see a rise in overall part weight. If the melt temperature were low, causing flash around the runner or center of the mold, you'd also see a rise in pressure at transfer and a drop in the overall part weight. If the flash was due to a high injection rate, you'd see an increase in part weight and pressure at transfer. Also, you'd note a shortened fill time. If the flash you were seeing was due to a low transfer set point, you would almost see identical symptoms, but you'd find an increase in the fill time rather than a decrease. If the flash was due to a high pack pressure and hold pressure, your fill weight would be the same, but the pack weight and final weight would increase. Although this is one of the first things people change when troubleshooting flash, in most cases, increasing clamp tonnage is used as a band-aid. In all likelihood, something else in the process has changed. If you're running a multi-cavity mold, you can often see a high imbalance where some cavities flash, while others intermittently short, and the fill time will vary. If this is the case, you may want to consider evaluating the cavity balance of the tool during filling. If the check ring is running inconsistently, you might have a tough time maintaining a constant fill, resulting in intermittent shorts and flash. This would be easily identified in a shot-to-shot change in part weight during fill. If your mold or platen was deflecting, your process outputs would change little, as with a low clamp pressure. The big difference here is that deflection and flash is most likely to occur in the center of the mold. If mold damage and wear happen to be the culprit, then you'd see flash in a particular spot in the mold. This would come up repeatedly, and this defect is most often the cause of when you're getting flash in a short shot.